Okay, thanks. So before we start today, how are we doing with Chapter 2? I'm assuming you've gone through a lot of problems in Chapter 2 at this point, which is the one for which I've given you solutions. Now, not all the problems have solutions in the manual I gave you. So if you tackle those with no solutions and you have any issues, same email, office hours, we can talk about them. We can solve them in my office. But you really should be, at this point, really confident with solving kinematics. And we studied kinetics not too long ago, but I'm assuming you're starting to look at those problems too in Chapter 3. Now, so far in kinetics, we have only mentioned the gravity force, which is said for most of the cases is a constant acceleration pointing in one direction. And so that's our model for gravity in most of the problems. And we've seen reactions that are mostly unknown forces, which we may need to solve for or not, depending on the problem. So what we'll start to do today, and we'll do for a couple of lectures, we'll formalize forces models. So we'll see some different models for forces, starting today with contact forces. In particular, we'll see two different models for friction. Now, what it is important to understand, especially as a graduate student, these are models. These are just things we make up to represent reality, and they're not reality. So they allow us to apply the principles we studied. They may represent realities in some special cases, but they're not reality. The same way as G is not the force of gravity. It's just an approximation where we assume that the Earth is flat and is inertially fixed, which is a lot of assumptions, right? But they may work for some cases. And again, they allow us to apply the principles and describe in a mathematical way what's going on. So let's see what we need here. And I really want to do a problem with the two types of friction forces that we're going to describe today. So these are the tools we need. We need the usual reference frame A with the coordinate system whose origin is fixed in A, and same for the basis. And then I define what is basically another reference frame, which is just a surface, rigid surface S. And so S, I'm going to start all the assumptions here. We have a rigid surface S, and let's say also that S is differentiable. For what we are concerned, this means that you can take its gradient. It's a smooth surface. There's no weird jumps or steps or things like that. So we have a particle of mass m, a particle of mass m, which is in continuous contact with S. Otherwise, what we're going to say doesn't make any sense. So there is a particle m here, which can move on the surface. It's not part of the surface, but it's touching the surface continuously. And we're going to call P the instantaneous point of contact. So P is a point on S. So as this particle m is moving on the surface, it's describing a trajectory on the surface. And every time we look at it, it's occupying a position which is the point P on S. But then the next time, it's a new P on S, right? OK, let's call the position of P R, just the vector R. So we have R is the position of P in A, pretty much, with respect to an observer fixed in A, in that coordinate system. Okay. All this to define a very simple vector, which is the relative velocity between the point mass, the particle mass m, and the surface. And we write it here. So definition, V rel. We'll discuss in a second why I'm not putting any superscript on the left-hand side. It is defined as the velocity of the particle m as seen by an observer in A minus the velocity of the point P, which is a point on the surface S as seen by an observer in A. So this is the definition of the relative velocity between the particle and the surface, on which basically it is sliding. Yes?
The letter P there on the fourth definition, R is the position
of P in A. Thank you. Yes. So again, imagine, just to make your life simple, this is S, the surface can be the table, and you have a point mass which moves on the table. And I'm trying to express the velocity between, that is basically seen by the surface as m moves on the surface. Now the surface itself can move. So the reference frame S can move as well. Remember, it's a rigid surface, so it's perfectly fine to hold that a reference frame as well. So that's the definition. Let's just quickly show that I don't need to write any superscript here, because that relative velocity is really independent of the reference frame in which I'm sitting and observing what's going on. So this A can be a B, can be a C, can be whatever you want. It's not going to change the result VREL. You get the same vector. Remember, a vector doesn't really care about reference frames and coordinate systems. The velocities and accelerations are computed with procedures that depend on the reference frame. But once you get the vector is independent of the reference frame. Now, well, one way to prove this is say that I'm looking at now the velocity of the particle of mass m and the point P from a B reference frame. I can write that Vm in B is Vm in A plus omega A B cross with, I'm calling rho the vector that goes from the origin of the coordinate system fixed in the reference frame B to the mass m, which will be the same for P. So if you do the same for VPS in B, this is going to be equal to VPS in A plus, so you can imagine where I'm going with this. If you subtract the two, you basically get that these two differences between vectors are equivalent. So it really doesn't matter in which reference frame you do it. It's independent. And if we start solving problems in a while, we'll see that that is true. It comes out from solving problems as well. So it's really frame independent. Independent. Now, we said at the beginning we don't want to do anything based on intuition in this class, but if you think about it, the way m is moving on the surface, it's really something that is between m and the surface. It shouldn't really matter if I'm looking at it from A or from B, from somewhere else. It really shouldn't. It should make sense, right? It's a relative velocity, so it's between m and the surface. And the surface in this case is represented by point P, which is where m is touching at every instant in time. So nothing special here. Let me add one more ingredient, and this is not supposed to make much sense because my drawing abilities are very minimal. But this is supposed to be the plane, tangent plane to S in P. That's why I said it's differentiable. So you can define always a tangent plane to the surface. So given that, this point and the surface are going to exchange some contact forces. That's what we're going to describe here. So if we don't need this, what we usually say or define is that the contact forces between M and S, they project, well, they can only project on the plane and perpendicular to the plane if we do it that way, right? So in the plane, call that T, let's call that plane T. So in the plane T, and these are called, what do you think these are called in the tangential plane? And that's a complicated drawing with the, this wavy surface and a point moving on it. But again, go back to the table. If it's a table and a particle here, the forces that they exchange with each other on the table, it's what you have called for years friction, right? So anything that is on T, we call it friction. And perpendicular to the plane, T is what we call, what do we call that? Yeah. Reaction. We have already used that term, actually. OK. This is what we want to model today. Two different types of friction. Do we need this anymore? I don't think we need all these. OK, so the first one is called Coulomb friction. Now keep in mind this is a dynamics class, so things need to be moving. All these definitions, the two definitions that I'll give you, they do not apply if there is no relative velocity between the two, the point of mass m, particle of mass m, and the surface. If there is no VREL, these two friction forces don't exist. We don't do static friction. Actually, static friction is undetermined. You have to solve for it in a static way, but we're doing dynamics here. So I don't focus on static friction. There must be a velocity between particle and surface. So the Coulomb friction, and this is a vector. Forces are vectors. We don't do scalars for forces, even though these types of forces are usually written down in books as scalars most of the times, which is terrible. OK, so force of friction is defined as some coefficient of Coulomb friction, mu, times the, I didn't define reaction, so I didn't give it a letter. So let's call force of friction f of f, as I just done there, and reaction, call it n as a normal, r, doesn't matter. The point is that this is the norm of the reaction force. And then we have VREL, vector, over the magnitude of VREL. Now again, this is a model. It does have something to do with reality, but the Coulomb friction, coefficient of friction, which here we assume is constant, that's what we do with problems, is not really constant. It changes with temperature, it changes with the surfaces you have, it does evolve. So this is an approximation of reality that we use to solve problems. But if it is an approximation, you're not allowed to make it simpler than this. That means when you talk about friction, this is what Coulomb friction, this is what you use. You don't use minus mu VREL, something like this, which looks like a scalar. You don't. It's a vector. Well, that's not usually what I've seen before. It's minus mu times n. That's what usually you see, because this is a unit vector here, of course. And so I've seen these for years, right? It's these pointing in a certain direction. That's not the way to do it. We do it with vectors. Now, the other comment that needs to be made here is about this direction of forces. We are used to saying that this is opposed to motion because there is a minus in front of VREL, which is okay, but it's not always true. Between a particle and a surface, yes, but the typical example that we should think about is wheels, your bicycle on the ground. If you bike, well, first of all, the wheel is not really just touching on a point. It's touching on several points, right? So if we use this kind of model and we allow it to work for all the points that are touching the ground, and I am biking so that the wheel goes this way, which way is the relative velocity? It's that way, right? So VREL is something like this, pointing that way, and so the force of friction is actually pointing the other way, which is why you can move. So it's not always opposed to motion. It depends on what it is that you define motion. I am trying to move with my bicycle, so I love VREL to be going backwards and so that the friction can push me forward. So that's true for the particle, but not in general. In real life, you cannot really say that the force of friction is always opposed to motion. If it wasn't, I would be in pretty sorry shape when I take my bicycle or drive my car, right? So that's one of them, Coulomb friction. That's the only one that we're going to use. The second model that we're going to see is, I don't think we need these anymore, is called viscose friction. And that was usually associated with drag forces, for example, when you talk about airplanes or flying, vehicles. It's a simpler model. So let's call this, if you want, we call this force of friction Coulomb, force of friction viscose. It's simply another constant times VREL. That's it. So same, if there is no relative velocity, this doesn't exist. The same for the Coulomb one. This is directly proportional to the velocity. As you're used to seeing with the drag forces, for example, but in that case it's a squared velocity. But after all, the drag force for an airplane is some type of force friction. So you can already think about the fact that these are all models. I mean, you can have a v squared here, you can have a v cubed here. This is done, actually. Different regimes of speeds may give you a better model. So you may say that this is valid up to a certain VREL, and then after a certain point, it breaks down. You need to change something in this model. They are models. That's what you do all the time as graduate students, use models. Maybe you develop your own models. Maybe that's part of your work, actually. OK, so there's really nothing special about these two, other than, underline again, these are vectors, and that's how they need to be used. They're no different from velocities and accelerations and everything we've seen so far. They're vectors. There's nothing else to say. Comments, questions about this before I jump into a problem, which you may have seen before, but I want to do it with both of them. No questions. OK. See what I have. I think we actually seen this at the beginning when we're doing just kinematics. These tube here with a particle inside of it that it's able to translate inside the tube, or arm. Let's call this the arm. This is the ground, which is inertial. Call this rotation point O, and this is my point P and particle mass M. There is no gravity, and instead of giving you an angle, I'm just giving you that there is a constant angular velocity, which is the angular velocity of the arm with respect to the ground, counterclockwise for us. And what else? Well, I'll call this distance r. Let's find the equations of motion for for M. Sorry, I want the differential equation. How many equations should I expect here? Should I write equations or equation of motion? Just one, right? Omega is a given. I give it to you. So the only thing that you really need is a differential equation in terms of r, this distance. Because if you can solve for that equation and give me r at all times, I have given you the omega, so you can tell me exactly where the particle is. That's the point of solving a differential equation in dynamics. Okay. That's what I want, differential equation of motion for M. And again, with Coulomb friction, and we'll do it with the viscose friction. Maybe we'll do the second first. It's easier. Okay. You tell me how to start here. At this point, you should know it. Kinematics. That's what we need to do at first. F equal ma with respect to the ground because it's inertial. That's what I start from. I have just two vectors that I need to compute. The first is the acceleration of p, of m, with respect to the ground, and then the forces. Okay, so to do the first part, which is kinematics, we start with reference frames. I mean, there's really nothing new here. And those are already there for you, but we don't skip steps. So we have G, which is the ground. And let's do the coordinate system here. What do you want to do? Origin at O. Let's say EX along OP at time equals 0, assuming that at time equals 0, it's pointing, as you can imagine, this way. That's what we do always. Rotation is counterclockwise, so probably I want to do EZ out of page, right? Y is EZ cross with EX, and I'm going to write with my finger pretty soon. Okay, so this is what I have. EX, EZ, EY, right? Okay. And then I have A, the arm. And there's nothing new here. Same origin. Origin at O. And then, as we've done several times before, let's say that ER is along OP. Reuse one of the axes, because that's the rotation axis. And E theta is EZ cross with ER. So this is not only big EZ, is also little EZ. And this is my ER. And this is my E theta. And this is, well, can't really name it with an angle other than omega t, right? Because I gave you omega directly. I didn't give you a theta angle, but that doesn't change anything. Yes?
Wouldn't it be clear if we said EX along OP at omega equals 0?
Omega cannot be z. I mean, if I give you that it's constant,
Between the two, I guess. Because t equals 0, you know, if you don't know the initial conditions.
Well, I assume that I know. Well, you definitely need to know initial conditions if you write the differential equations of motion. Otherwise, they're pointless. Again, we never get to the point of integrating those differential equations. This is not the point of the class. So we'll never continue after we find differential equations with saying, okay, now solve it, numerically or analytically if possible. But it is assumed that you're given initial conditions. And I'm probably just skipping those steps. But in most of the problems, I'm assuming that they're known. And so I can set my clock to be t equals 0 when this arm is down here. I mean, I can do whatever I want.
Even if it isn't, I don't think it makes sense.
Yeah, no. Make sense? So again, we get to differential equations of motion. We're not going to solve them unless it's really needed and unless it's a very simple case. Okay, so those are my coordinate systems. You tell me how to find the velocity and acceleration. Let's start with the mass m. V of m, because remember now I will have to compute the relative velocity, so I have to do it for m and then for p. And m and p are two different things. M can change its r. P is the instantaneous point of contact, so the velocity of p, as we'll see, will be computed with fixed r, because p is a point that is part of the arm. It's the point of contact at that time, but that's how you compute it. The relative velocity is given as velocity of m as seen by basically any reference frame minus the velocity of p as part of s with respect to the same reference frame. And again, this a can be b, c, whatever. It doesn't change the VREL that you're going to find. This has a meaning. It means that I'm looking at where m is on that surface. The surface is now the inside of the tube. Is that location, and I look at that location as part of the surface. M is the one that can move. P cannot. It will be a new P at the next instant in time, but that's how I compute this part of the velocity. Make sense?
So this P will be constant for all values of M?
No. The VP S in A will be a certain value at this particular R. It will be a new value at another R, etc., but you will not see the term with R dot in here. We'll do it, and we'll see. Again, think about simple examples. Think about this table and something moving on the table. The table is not moving with respect to you. You are the reference frame A, so this goes to 0, because no point on the table is actually moving with respect to you. But if it was moving, then you will have to take into account the motion of the surface, and that's what we do here with this VP S in A.
But since the whole surface is moving at a particular velocity, wouldn't that be a constant? Like if it
Well, it's not.
location in this
So if you have a bar that is rotating about this axis, this point P and you are looking at it from the ground, this point P has definitely a different velocity than this point P and this point P. They are farther away from the rotation point.
in translational motion, in that case it will be constant.
Well, if the surface S is just translating entirely with respect to your reference frame, yes, then all points will have the same velocity. Yeah. So in this example, my surface S on which the particle of mass m is moving happens to be a tube. There's nothing wrong with that. It can be a tube. It's just not a fancy wavy surface in 3D. It's just a tube, but it doesn't change the way I approach the problem, right? Okay. So since I can do this in any reference frame, well, let's pick the ground. So what is the velocity of the particle m as seen by an observer fixed to the ground? Right? Plus omega a g cross with r of m. Make sense? What is the velocity of the particle of mass m with respect to the arm? It can move. Yes, that's r dot little er plus, well, omega is actually given. It's omega ez, right? This is the norm of the vector omega. I know it's positive on the direction of ez. That's why I picked ez that way. Cross with r er. And so this is r dot er. What is ez cross with er? Is e theta, right? R omega e theta. This is clear, right? You can stop me anytime if any of the steps is not clear, as always. Now, this takes care of this first velocity, right? We said it doesn't matter which is the reference frame. Let's do the second one now. So I will compute it anyways later. The second is the velocity of P as part of the arm seen by the ground, right? How would you compute that? So now P, it's a point on the arm at a distance r from the ground. So you can do the same. You can say that this is d dt in g of rp, which is equal to d dt in a of rp plus omega a g cross rp. Now, rp and rm are the same vector. I agree with that. But in the case of p, the magnitude of r is not allowed to change because I treat it as a point. It's a definition. I define the relative velocity that way. I treat it as a point part of A. So this is 0. Make sense? And so this is going to be r omega e theta. And look at what we get, actually, when I compute the velocity between the two, the relative velocity, the way I defined it. So it's going to be the first vector minus this vector. I get r dot little er. That makes perfect sense. It's the velocity between the point, the particle mass m and the surface. That's how it moves with respect to the surface. It just goes along r. I could have probably just guessed it without doing any calculation. But we don't guess. We apply the few formulas or principles that we have. But yes, you could have guessed it. If you're sitting with the arm, that's all you see, r dot er. Okay. Any questions about this? This is important. It's like the rolling. The rolling has 3 points overlapping. 1 point which is belonging to the first rigid body, 1 point which is belonging to the other rigid body, and then that point that is going to describe in space the instantaneous point of contact trajectory. There are 3 different points. The 2 points on the rigid bodies that touch each other at a certain instant will not touch each other at the next instant in time. And this is the same. At this instant, the particle mass m is sitting here, which happens to be called point P on the arm. Then the next time instant will be probably up here or down. And so we are looking at a new P prime on the arm, right? Okay. Well, then we're not done actually. I need the acceleration, right? But this is good. I need it for the 2 models of forces. So I'd better put it down here. I don't think it's going to be hard to remember. VREL is r dot little er, and that's nice. That's done once and for all. So I don't really need these anymore. I just need to finish computing the acceleration of the mass m with respect to the ground, which is going to be d dt in g of that vector vm in g, which is, if I apply the transport theorem, d dt in a of vm in g plus omega a g cross with the same vector. Okay, so what is the first one? d dt in a of vg of vmg. So if I am in a, I don't see little er and I don't see theta changing. So I get an r double dot little er. Remember, this is constant. So r dot omega e theta, and that takes care of the first rate of change. And then I have same, omega is the same, omega little ez, which is crossed with this entire vector here, r dot little er plus r omega e theta. And that is going to give me, I should really request a slightly higher board here next time, plus r dot omega e theta. Okay, what do we have? Ez cross with the r is e theta, so plus another one of these, r dot omega e theta. And then I have Ez cross with e theta, which is minus er, minus r omega dot er. So in the end, what I really need is just the acceleration. So I can erase all this if you don't mind. Acceleration of m in g is the following vector. Let's try to put it all together. R double dot minus r omega squared little r plus 2 r dot omega e theta. Done.
Question.
Yes.
We did this one after taking Vn, relative velocity, this one, that's it. We're finding An. Can't we do it by taking the V relative directly?
I'm not sure I understand the question. I'm sorry.
I
So,
always had this question, why can't we just take out the relative acceleration by, yeah.
well, this is not, I'm not computing the relative acceleration. For the model forces I gave you, I just need the relative velocity. I didn't talk about relative acceleration. I don't need that in those models.
But cannot we find out the force with the help of relative acceleration if we had relative acceleration?
You do have a relative acceleration, but I don't need it for anything here. So I need kinematics, which is this part. And for kinematics, if I want to apply F equal ma in an inertial reference frame, I need to find the acceleration of the particle of mass m in that inertial reference frame. There's nothing that really changes there. And then for the side of the forces, if I'm telling you that you have viscous force or Coulomb friction forces, viscous or Coulomb, you just need this vector. You don't need the relative acceleration. You can compute it. It's probably going to be r double dot er, yeah. But I don't know what you can do with that in this problem. Because the m, so this is really what we're going to do, right? As we've done last time, we're going to write this vector equation. And so we've done this, done. And here you will have, you will have the reaction that we may need to solve or not. And then you will have the Coulomb forces, but in none of them the relative acceleration is needed. I don't know if that answers your question. If I had come up with a model that has the force as function of the relative acceleration, that would be a little weird. It is possible, but never seen it for friction. So, okay, let's do it with which one do you want to do first? Well, first we need to do the following. Free body diagram. Here the procedure is really always the same. It's nothing we are making up. So if this is our particle m, there is no gravity. Which forces do I see? Say this is the direction ER, right? Which forces do I have? Friction, which I don't know which way is pointing actually. So force of friction, I'm not going to write which model I'm using. One of the two. And then reaction, which I think I called N. I called R before, I'm calling it N here, doesn't matter. For both of them at this point I have no idea which way they're pointing. I just know the line of action. One is N is perpendicular to ER, must be, right? And the force of friction is along ER.
No centrifugal force? No centrifugal force?
We don't talk about centrifugal forces. I mean, you can, but that is the way to do dynamics that will lead to a lot of confusion. This is your, okay, let's see, centrifugal force, it will be this. It will be this. So basically what is going to happen is that we write this, right? We write force of friction plus the reaction is going to be equal to m, all that stuff, r double dot minus r omega squared little er plus m2 r dot omega e theta. And then at some point someone writing books on dynamics said, just to make things a little more fun, I'm going to take some of these accelerations and move them on the other side. And for example, m r omega squared er equal all the rest. And they said, oh, this is the centrifugal, whatever it's called, centripetal force. Centrifugal in this case, right? I don't know what it is. I don't need to know what it is because it doesn't exist. All the real forces that are acting on this particle are the force of friction and the reaction from the sleeve, the tube, whatever it is. And there is no gravity here, yeah, which we don't have. So, but I've studied dynamics myself for years this way, trying to remember all these formulas for the centrifugal force, the Coriolis force, and what else do you have? Well, the term that is due to the fact that you are using a coordinate system which is translating maybe. So the acceleration of the origin of that coordinate system. That makes your brain like think about 2 million things at the same time, which you don't have to. Because all those weird forces, apparent forces, are already here. They're just mass times accelerations. And those accelerations are due to the fact that you're writing the inertial acceleration in a coordinate system which is not fixed with the inertial frame.
So that's not a real force.
This is no. What generates a centrifugal force, really? I mean, I can see a real force between two objects that touch each other. I know that planets attract me, so that I see gravity, but what is a centrifugal force?
Tendency to remain in orbit. Tendency to remain.
That's a way to explain it, but that I think introduces a lot of unnecessary definitions and confusion that it's actually right here. You get it every time you write your inertial acceleration in a coordinate system which is fixed to a non-inertial reference frame. That's what is happening, right? The reference frame fixed with the arm is rotating, so definitely non-inertial. And so I write the acceleration of the mass m in g in that coordinate system, and so I get those extra terms. If you want, what you can do is write the position of mass m directly in ex and ey, and take the derivative of that twice, and you don't need to talk about centrifugal forces.
What about if you have...
But I'm using the transport theorem, so I do get, results in coordinate systems that are not fixed to the inertial frame.
If you have a particle attached to a string or something that's rotating by that, doesn't it create a reaction? A tension reaction of the thing?
If there was...
No, I'm not talking about that model. I'm talking about a different model where you just take something and you start rotating with the...
So you have a string and you start rotating something?
Yeah, and you can feel like there's something...
Well, you are the one applying a force, you're pulling on that string, and you're making the velocity change. You are the one pulling all the time. That's what planets do. They pull on something flying all the time. They're constantly falling because the satellite wants to go straight, but there's something that pulls, that changes the velocity, and it keeps changing direction because acceleration is a vector, and it changes another vector, which is the velocity vector. So there is nothing wrong with these, defining other forces in principle. I really don't see the reason why, because they really come anyways from here. So rather than memorizing their expressions and try to plug in stuff in those expressions, you just compute the inertial acceleration, and they come out from there. Is this clear to everyone? That's the best way to do it. But it's less prone to errors. That's my point. Okay, so let's, I kind of did it here, but I want to do it a little slower if we can. I don't know if we get to do it. Let's see. Okay, so, this side of the equation is done. So f is going to be f of f. Let's do it with the viscous one first, plus n. Help me writing this. What is the viscous one? Is minus c Virel, right? R dot ER. And how do I write? I know that my R's look like V's. Sorry. How do you write N? I want to say N E theta. I don't know anything else. Again, the sign will come up by solving the problem. I don't know which way it's pointing. And so this is equal to this expression. So I have minus C R dot little er plus N little e theta, which is equal to, it's already in the right order, R double dot, there is a mass here, minus R omega squared little er plus 2mr dot omega e theta. Now, I want the differential equation of motion. What is the unknown here at this point? Which is the only thing I don't know? R, you mean which R? Little r? I want to find an equation with the derivatives of r. So that is not really the unknown.
N is 0?
N is not 0, but I don't care because I see it appearing here So n is equal to this. That would be an equation where you can solve for n, but these two by themselves don't have anything that I don't know. Omega is given, c is a constant, the mass is known. So my differential equation of motion in this case is m r double dot minus r omega squared, that's it for that side, equals minus c r dot, which you can rearrange in any way you want. But I don't see anything else other than r dot, r double dot. The other things are constants, and you better have initial conditions if you want to integrate that and give a r in time, but we don't do that. Now this was the easy one. Now if I do the other one, which is not that much harder, I don't think we need all these anymore. Okay, so if I do now the Coulomb force plus n, which is what I would have with the other model, I see a minus mu norm of n. VREL was r dot er over its norm. What is the norm of this? R dot. So let me write it actually like this. Okay. Plus n e theta. Okay. Now this makes things a little more complicated, right? Because r dot can be positive, negative. What would you do here? Well, the equation, if I write it all together, is minus mu norm of n r dot little er over r dot little er, the magnitude of this, plus n e theta is equal to same m r double dot minus r omega squared little er plus 2m r dot omega e theta. Now what do we do? Now we're in trouble. N is all over the place. What should we do?
Take in from E theta and substitute.
Take it from which one? The second, the one on E theta?
Yeah, the one with E.
So this, if I look at these two, I have n equal to m r dot omega. Okay. That's nice. I have an equation for n. What is the norm of n? The vector. I'm sorry, this is a vector. See? Make mistakes I shouldn't make. That's the magnitude of a vector. What is the magnitude of n? Well, this can be positive or negative, right? When I talk about the magnitude of a vector, I want to see a positive number, right? So I want to say that this is probably 2m r dot omega when r dot is greater than 0. I think you have to do two cases, right? Yeah, but how do you, I mean, you can write it that way in the equation. Yeah, why not? But so yeah, this is absolute value of but still, an absolute value forces you to write two equations. That's really the point here. Okay, so that takes care of, basically I've used this information and this information, so I want to stick it in here. What do you do? What about this ratio here?
Signal function about that particular.
Yeah, because this will be, this is going to be, you can write it this way, right? As well. So that is the sign of r dot. Yep. Okay, we're done. Sign of r dot. And then this is equal to m r double dot minus r omega squared. I think that's all we have. That's your differential equation of motion. It's a little ugly. You basically have to split it in two, and if you integrate this numerically, you have to have a check where r dot goes to plus or minus, positive or negative, what happens. And think about this. R dot positive means you're going away, r dot negative means you're going towards the point O. Just think about the two cases and see if they make sense to you. We can probably comment a little more next time. Okay?